now we have our second speaker for the session, Dr. Gavin Brennen from Macquarie University in Sydney. The floor is yours.
Thank you, and thanks for sticking around for, I know everyone's hungry. So this is some work that was done together with my postdoc, Gopi Krishnan and Murul Aludin. Peter Rohde, who used to be at UTS but has now moved over to BTQ. Deepesh Singh at University of Queensland, and Boshong Fu, who's at University of Melbourne. And this was done in collaboration with a team at BTQ Technologies. This was a company that was co-founded by cryptographers, and they've been interested on, saving energy in classical processing for post-quantum cryptography, but they're also interested in saving energy using potentially new quantum technologies. Okay, so the problem I'm going to be talking about is basically coming down to the problem of how do you reach consensus among a bunch of players who maybe don't agree with each other and there's no centralized authority. In this case, it's just like deciding the majority decision of what to drink, and there is this teetotaler here who's highly connected on the network and could try to convince everyone to drink tea when in fact the correct answer is beer. And so you want to make sure you get the correct answer. So we're going to see how to use computational processes to realize that. Okay, so I'm going to be focusing on a mechanism for reaching consensus known as proof of work. And the idea here is to be working in a network with many nodes, and we're going to refer to the nodes as miners because that's what's done in the literature. There is a notion of actually performing work like a miner would do. And the idea is that the miners on the network are allowed to be rewarded for the lucrative task of verifying a proposed block of new data. And how this works is that you propose a problem to the network that requires some computational effort to solve, but whose solution is easy to check. And fortunately, computer scientists have devised such functions that do this. That is, they're called one-way functions. So you're given a function f, and given some output y, find x so that f of x equals y. And you want this to be hard to solve, but easy to check. And such one-way functions do exist, and maybe one of the most famous one is hashing. So hashing is something that is very sensitive to the input. Like in this example, if I choose this sentence, the quick brown fox jumps over the lazy dog, and hash that, I get something that looks very random. And if I just replace dog with cog, I get a completely different output. So it's extremely sensitive to the input. And it also has a property that finding collisions are rare. So finding two inputs that give the same output is a rare occurrence. All right, so the idea of using one-way functions to help us in computational problems, particularly in the sense of sort of verifying transactions, actually goes back to some work in '92 by Cynthia Dwork and Moni Naur on a paper which was aimed to fight spam. So even back in '92, people were sick of spam. Couldn't imagine what it's like now. But the idea is to actually penalize senders from just spamming everyone by making them perform a little bit of computational effort when you send an email. So the idea is that if you have an email recipient, you would list that with a header along with a date and time stamp, and then you'd attach a little bit of a random string, which is supplanted here at the end of the header, indicated in these red digits. And you take the hash of this header, and if the hash has the first 20 bits equal to 0, then that's referred to as an acceptable header. And you can send the email, and the recipient of the email can check whether indeed that hash does have the first 20 bits equal to 0. And if it does, they'll take it. If not, they'll ditch it immediately. And the idea is that a spammer would have to spend some computational effort performing these hashes. And it may not matter for just sending it to a few friends and family, but if you're going to send it to millions of people, it becomes costly. So this is a way to actually make spammers pay. And this same kind of idea is integrated into the Bitcoin network. So here, the idea is that you want to add new transactions onto a network, which could include, transferring Bitcoin back and forth, buying products, and in order to verify a new block of proposed transactions, the miners on the network have to perform this hashing, where they add in some random bits, which are known as nonces, indicated here in this red section. They take a hash of the header information, which includes information about the transactions in the proposed block, add in this nonce, hash it, and see if the output has enough leading zeros. If it does, then they win, and they're able to verify the block. If it doesn't, they have to try again. And on average, they'll need to try many such random nonces to find a hash that will verify this block. That's referred to as Nakamoto consensus. Okay, well, this is being done a lot now. So this is just data from earlier today. These are the top 10 cryptocurrencies that use this kind of proof of work mechanism in order to verify transactions. And it's a lot of them that are doing it. It's like over 50% of cryptocurrencies do use this kind of consensus mechanism. And it's, well, for what it's worth, today it has a market cap of over 700 billion. But I do think what's interesting is the number 6 cryptocurrency on here, referred to as Kaspa, actually recognizing the energy cost to doing all this hashing, has decided that they want to integrate something known as optical proof of work, which is using physical photonic circuits to perform mesh-based matrix vector multiplication in the middle of a mining activity, which they claim will offer up to a 14 times speed up relative to using standard GPUs. This is not using a quantum circuit, but it's using a photonic circuit to perform multiplication faster than you could do with a GPU for the given amount of energy cost. But why is it so costly to do this hashing? Well, what's happened is that there is a whole industry of algorithm-specific integrated circuits, also known as ASICs, that do hashing extremely fast. Here's just an example you can buy on Amazon for about $8,900 US that performs 166 terahashes per second. And it consumes a lot of energy. It consumes over 3 kilowatts of power. And that's all it does, just does these stupid hashings. No other utility besides that. It'll heat up your house. Some people have actually run kind of saunas off these things. But it does it, and it does it very well, but it's very energy intensive. A single Bitcoin transaction, as of today, is consuming roughly the US household energy equivalent of 22.7 days. So that's a lot of energy to verify a block of transactions. And in 22, the Bitcoin network consumed the electrical energy amounts equivalents of the country of Sweden. So this is clearly not a sustainable practice. And there are cryptocurrencies which do not use proof of work, the most famous being Ethereum, which is number 2 in market capitalization. However, that one uses something called proof of stake. However, there are some reasons to not prefer that. There are some attacks that can be made, like long-range attacks or nothing at stake attacks, which make them less preferred by many users, as opposed to proof of work, which has historically worked very well and has some provable security to it. Another issue with the proof of work schemes used now, as on top of the energy cost, is that they're not quantum future-proofed. So proof of work is designed to be what's known as a progress-free computation. That is, the hash problem has no structure, so your chance to solve the inverse problem is essentially independent of prior work. You're just basically just randomly trying out strings. probability of success grows linearly with the time spent. However, you can use Grover's algorithm, if you had a quantum computer, to get a quadratic speedup. And particularly, the probability of success grows like sine squared of the number of steps taken. So this is nonlinear. And what are the consequences of that? Well, if you have superlinear scaling of a computational process for one of these proof of work problems, what you can do is you can decide to measure your register early. You know, you don't have to wait until you reach the target solution here. You could just say, okay, well, I might win with some chance. I'm going to measure my register now, and I can check to see whether I got the right answer quickly. If I do, I win. If I don't, okay, I have to restart. But if you're competing against a bunch of other miners and there's a profit to be made, there actually is an incentive to measure early. There's a very nice paper by a team who was at CQT, just down the road, with Miklos Santa and Troy Lee, where they looked at what they call quantum races, where you have lots of quantum computers all running the same problem, but you want to be the one who finishes first. And in fact, it turns out there's a Nash equilibrium which develops for different measuring times where you probabilistically choose to measure your register early. And the effect of this on the network will introduce large fluctuations in the time to solve. So I actually, especially if you're a student, I strongly encourage you to have a look at this paper. It's quite fun to read. And I think it opens up new ways of thinking about how we'll actually use quantum algorithms in a context where time to solve matters, not just when you eventually solve it. If there's profit to be made, people will come up with strategies to maximize that profit. So what we need to do is we need to find better ways to solve these proof of work protocols that use quantum technologies but would be more energy efficient. So we've been looking at using what we call quantum proof of work. And you know, a natural try here would be to find a problem in NP that quantum computers can solve quickly. So an example is factoring, right? You could pose, you know, large numbers to be factored. Someone does it on their quantum computer, announces it. You can quickly check it on a classical computer, and if that checks out, then they could say they verified the block and you're done. However, such problems require universal fault-tolerant quantum computers, which are still several years away, and it's likely they'll be costly to access for the amount of time you need to solve such a problem that would restrict the participation in such a network. So another problem, or another approach to this, is to use quantum sampling problems on non-fault tolerant devices. This could include things like the IQP protocols, instantaneous quantum polytime, on quantum computers, or boson sampling. So we focused on boson sampling. This is just a photo of a boson sampler. And here's the idea. So you've got your boson sampler, which basically consists of an interferometer describing a unitary U, some input configuration of photons, and some output that you measure. And the choice of where we put these input photons, which modes we put them in, will be determined by the block header information. So it's something you can't predict ahead of time. So you have this input state, you permute the input state depending on the block header, runs through the interferometer. It's just a linear transformation, and then you get an output state which is going to be a large superposition over the different multi-Fock output states for the system. There are an exponentially large number of terms in this superposition, and each amplitude of the output state is proportional to the permanence of a matrix, specifically for an n photon input state. It's an n by n submatrix of the unitary U, formed by taking copies of each row and each column according to the multi-photon output configurations. All right, well, the reason that this problem has been studied so much is that it has beautiful simplicity and also complexity. It's known that, there is a gap in the complexity of computing permanents versus determinants. So the permanent of an n by n complex matrix is just given by this sum over products of elements of the matrix which have been permuted. And the complexity class is sharp P hard, even for a multiplicative approximation error. So this is an exponentially hard problem in the size of the matrix. Whereas the determinant, where you have these -1 factors that show up according to the parity of the permutation, is solvable in polytime, particularly n cubed. Now, boson samplers can't actually solve for permanence themselves, because you're always getting some random outcome when you measure these things. You don't get any shortcuts in breaking these complexity classes with a quantum boson sampler. However, the output distribution cannot be efficiently simulated by classical computers due to a famous result by Aronson-Okhropov over 10 years ago now. In fact, the best known classical algorithm to compute a permanent is Reiser's algorithm, which scales like n times 2 to the n. But let's go ahead and work out what would be the classical sampling rate if you wanted to use classical computers to do this task. Well, first off, it seems obscenely hard. You've got an exponential number of amplitudes, and each amplitude is exponentially hard to compute. But, important lesson, we should never underestimate the power of classical computing. There are some very clever people out there who've been thinking about these problems for a very long time. You don't actually have to compute an exponential number of these samples. You can use importance sampling. So this is the idea where you take an easy to estimate distribution, you sample from that, take a ratio of the probability to get the point in the hard to estimate distribution divided by the probability for the point you're at to the easy one. Use that to estimate your next Markov move further on in the distribution, and you can actually converge rather quickly to a path which will sample efficiently and accurately from the hard distribution, although each point you do is still going to be exponentially hard for this case. And remarkably, there is a result using hierarchical sampling by Clifford and Clifford back in 2018, which shows that you can actually get away with only using on average about 2 permanent evaluations per sample, which is quite remarkable. In the end, what this gives us is that the classical sampling rate, it would be scaling like this 1 over a tilde, where a tilde is the time to compute a single n by n complex permanent, a complex matrix permanent on a classical computer. And then there's a Reiser factor of n times 2 to the n. What are these a tildes? Well, if you're using a single core Xeon processor at 3.5 gigahertz with 128 gigabytes RAM, there was actually a paper written on this which showed this is about 10 to the minus 9.2 seconds. And on the Tiana 2 supercomputer using 16,000 nodes, it was 2n times 10 to the minus 15 seconds. This extra n factor here is arising because it wasn't possible for them to parallelize their Reiser's algorithm. All right, let's look at the quantum sample rate. Boson samplers experience photon loss, and if we post-select only on those outcomes where the number of output photons equals the number of input photons, and we also assume that we're propagating through m equals n squared beam splitters. So we have a number of modes which is the square of the number of photons, which is basically enough to ensure that you don't get collisions that occur. Then you get a quantum sample rate, which will scale like this eta f, which is an overall efficiency, which is a product of the photon generation efficiency, the coupling efficiency, the detector efficiency to the nth power, times eta t, which is the beam splitter transmission probability, to the m times nth power, times a bare single photon source rate divided by n. Now, I'm going to assume some optimistic specifications, and I'm happy to talk to experimentalists afterwards. I don't think these are insane, but they clearly are optimistic. I'm going to assume that the A to F parameter here is 0.9. The transmission probability is 0.9999, and the single photon source rate is 100 megahertz. These aren't too wildly off some already reported figures. Obviously, these were on devices that people spend a lot of money and time on, but it's not crazy. So here are the kind of plots you get on the comparisons. So we can look at the speed up you get from quantum boson samplers versus a single core processor or versus a supercomputer. And you see that, when you're on, when you're in the region between 10 and 20 photons, n is on the horizontal axis here, you're clearly doing much better than a single core processor. And you really only beat the supercomputer after, you're in the mid-20s. But what's interesting is if you look at the energy cost, and what I'm using here as a metric is energy in joules per sample. I kind of like this unit. It's actually putting an energy cost to a computational problem, a sampling. And we'll look at the cost in energy per sample for a supercomputer, the Tiana 2 supercomputer, which has a power of 24 megawatts. The single core processor, which is about 100 watts. And for the boson sampler, I'm just going to assume it's 1.5 kilowatts, assuming that the energy is dominated by the cryocooler for the single photon detectors. And I'd really be happy to talk to experimentalists to see if there's a way to make this better, cleaner assumptions. But this is what I got from literature and we talked to a couple experimentalists on this. But this is notice this is a log plot here, log scaling. And so when you're around the region of 20 photons, you're several orders of magnitude more efficient in producing these samples, as well as being faster, particularly for the single core processors. So we're going to integrate these schemes into a protocol for proof of work. So it's a multi-stage process, and I'll just take you through the steps. The first step is a transaction is created on the network. People want to buy and sell things. A new block representing the transaction is created. This is called the candidate block. It's the gray block here. It hasn't been accepted yet. People have to do some work to accept it. This new block is sent to every node of the network, and all nodes will stake some tokens to participate. The staking is actually important, as we'll see just a little bit later on. This makes it different from networks like Bitcoin, where you can just go ahead and immediately start on the problem. Here, we're going to make sure that people put in some stake. Then the miners implement boson sampling for some predetermined amount of time with an input state that's dependent on the block header. And they commit all their samples. So they cryptographically commit these samples and send them to the rest of the members of the network. Doing that ensures that they can't change what they said they committed, what they announced earlier, and also avoids the issue of duplications, where you might just have someone copy someone else's samples and send it. The next step is all contributed samples are combined to create a net sample set, and these are binned according to a strategy stipulated by a random beacon. Following a validation procedure of bin samples, all honest verifiers of the network are rewarded for their proof of work and have their stakes returned. Dishonest verifiers are penalized and lose their stake. And finally, the new block is added to the blockchain. Okay, so how does this work? Well, the crux of the problem is that there is no efficient way to verify full boson sampling. And this has been something that's been going on in literature for quite a few years now. How do you know if someone actually has a boson sampler? Everything looks quite random. And how do you know they're not just using some classical device which is pretending to put out boson samples? Well, the trick is you can use coarse graining. So in the upper right here is a plot of the full distribution of a boson sampler with 2 photons and 6 modes. So there's all these different output possibilities for the Fock state distributions. And we consider 2 types of binning, which do coarse graining. One is referred to mode binning. Here I've got 3 modes, and I look at the distribution for photon counts in those bins. And another one is referred to as state binning, where I group possible different Fock state outputs and collect them all into a single bin. So here, like on the top full distribution, I have these 3 orange outputs. Those go into a single net state bin, given by that single orange bar. All right, so how does this actually work? Well, the point is that you can actually validate mode bin distributions in a polynomial number of time. So we consider a multiphoton binned number output, which is, each point refers to the number seen in each one of your mode bins. And then you can write a mode bin distribution as basically a Fourier transform over a characteristic function, where the characteristic function involves computing the permanent of some n by n complex matrix. So to estimate this mode bin distribution, you need to estimate on the order of n to the number of mode bin permanents. Now, I mentioned earlier that each permanent requires an exponential amount of effort to compute. But key here is we don't actually have to have it exactly. We can estimate it. So if we only demand a polynomial additive approximation to the mode bin distribution, then we can use something like the Gurvitz approximation to permanence, where you can estimate a permanent using basically averaging over computing products of matrix elements, choosing random binary vectors, and it turns out that the number of steps you need in order to achieve this with a additive error of delta goes like n squared over delta squared, which is polynomial if delta is bounded. So what we'll do for our validation is we'll say, okay, everyone can go off and compute classically what the mode bin distribution should be after they know what the binning is, compare it to those committed samples, and if it's less than some pre-prescribed tolerance, we'll say, yes, you are an honest boson sampler. If not, you are a dishonest one, and you lose your stake. By the way, where are we at with time? Okay, great. How many samples do you need in order to validate? Well, there's a closed form upper bound you can get, some based upon solution results. But it turns out numerically you can actually do much better than this upper bound. And so like for 6 mode bins with 10 photons and 100 modes, you can get by with a few 100,000 samples. And what's important is that the distributions you get of the mode bin distributions are highly distinct for different input choices, which depend on the block header, and output binnings, which is determined by the random beacon. So you can't pre-compute, and you're able to distinguish people who are cheating from people who are honest boson samplers. I won't have time to go through this, but it turns out that you can show that if you have this staking as well as a reward, if you choose the penalty to be between 1/3 of the reward and the reward, then you get a Nash equilibrium which incentivizes honest players for participating and dishonest ones from not. And just one last point here, you can actually modify this protocol to work with Gaussian boson sampling as well. And actually the validation is even easier because it works, turns out you can compute the characteristic function using determinants. So I'll just close with this. We've taken a problem which honestly is useless. Boson sampling is really useless. And we're using it for a task which currently classical computers have a problem which is useless. But it does what you want it to do. It proves people have put computational effort in. It incentivizes boson samplers, and importantly, it has strong complexity theory arguments that classical computers will not be able to speed things up. And we get a significant energy improvement. So the open problem is, could we actually design an interferometer so that we could actually solve a useful problem for this? But that's future work. Thanks.
Okay, thank you. Right. We've got time for maybe one quick question, and then we can move on to lunch after that. Anyone has any burning, urgent questions? Okay, over there. Thank you.
Hello, thank you for the talk. It was very interesting. I was wondering, when you spoke about the energy consumption of the boson sampler, do you know how it will depend on the block header? Because if you're using, for example, thermal phase shifters to make the boson sampler, they can really consume a lot of energy depending on the state you want to implement.
So what we've assumed here is that, at least for several block periods, you would use the same input or same interferometer. So that wouldn't have to be changed at all. The only thing that would have to change is where you put the photons in. Now, how easy that is to modify, I'm not sure. Yeah, so I'd be happy to talk to you or others who have ideas on how that's done.
Okay, thank you.
Okay, great. Let's thank Gavin again. And quick announcement is lunch is outside. Please be back around 2 p.m. To start our next session. Thank you.